So in our last application, again, this is Galen Pickett, Cal State University Long Beach, Physics 151. In our last application, we determined that an object which initially starts at rest, so v is equal to 0, it falls for a time delta t, the distance it goes is, so write that as delta z is equal to minus 1/2 weight divided by mass delta t squared. This was a combination of the momentum principle to tell us how the momentum of the system changes, and the averaging of the velocity, which is just a geometric and mathematics idea, which cannot go wrong as long as the forces don't change their magnitude or direction, and then position update idea. And this is a fundamental statement that is always true: how objects travel, how objects move. So we know how far it's gone, we know how long it's taken, we even know how fast it's going. There's one extra piece of information that we've got, and it is from a different experiment entirely, one that you have no doubt heard of. So you go to a Renaissance tower that was had a badly constructed foundation in Italy, in the Italian city of Pisa, and your name is Galileo. You take a large object of mass capital M, say a cannonball, and a small object of mass little m, say a bullet, and you release them at rest from the same time. And you notice that these objects hit the ground at the same time with the same final velocity. Now they've got radically different momenta. There's a lot of momentum on this one. That's like the car that you do not want to get hit with. This one's like the ping pong ball that you wouldn't mind getting hit with. They've got radically different masses. So they've got the same velocities but different momenta. And not only do they hit the ground at the same time, it's not like the small one rushes ahead and then slows down, and the big one starts slowly and then catches up, and it's just a tie at the end. At every spot, so you can stand here on the second to the top floor, and you see these two objects go past you at the same time. You can stand here, they're also past your level at the same time, and they hit the ground at the same time. You can prove that to yourself in a little experiment. You take two objects, a big one and a small one. And these are just two objects that you are convinced have different masses. So, say a quarter and a penny. Now, hold these two objects so that the bottom, so there's your quarter and there's a penny. Hold them so that their bottoms are at the same level. You don't want to hold them so that their tops are at the same level, because then the bottom of the quarter will always hit first. And then you pick some height, let's say 1/2 of a meter. So that's 2 feet, 1.5 feet, something like that. You release them at the same time, and then you listen for some sound when these two things hit. The quarter makes a slightly different sound than the penny, and you'll be able to judge which one hits the ground first. And then you change this distance. So instead of dropping them from 1/2 a meter, you drop them from 1 meter, and you do the experiment again. You make yourself a little table here. Trials, let's say 1, 2, 3, and heights, height number 1, height number 2, height number 3. You can make yourself a little table, and in each of these, so this is 9 different experiments you do, you can write whether the big object or the little object hit first. So big, little, 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 big, little. And whatever your data looks like, if it looks like some random mishmash of big and little, then at each one of these heights, you can't really tell which one hit the ground first. Proving for yourself, in a small experiment, that that actually occurs. Now what that means is, so let's let R1 stand for the position of as a function of time, this is the position of the big object. And let's let R2, as a function of time, be the position of the small object. We know that R1 and R2 are the same things because they're always at the same, they start in the same spot, they stay at the same height, they stay at the same height, and they hit the ground at the same time. Now if that's true, we've already figured out what those are. So for the big object, we've got r1 as a function of time is, and I'll write it this way, minus the magnitude of the weight divided by the mass times 1/2 times t squared, and then a z hat. So the z hat is a vector that points upward. It's a unit vector. The minus sign means downward, so r1 starts from this origin, and it's negative. R2, and that is the weight on object number 1 divided by the mass of object number 1. The position of the first object depends on what's the weight and the mass of the first object. For r number 2, the small object, as a function of time, that's equal to the weight of the second object divided by its mass, again with a minus sign, with the 1/2 times the t squared and the z hat. And those two things have to be equal for them to hit the ground at the same time. So in other words, we've got this and this are the same functions of time, which means that minus weight 1 divided by m1 times 1/2 times t squared, if I just look at the z components of this equation, is equal to minus w2 over m2 times 1/2 times t squared. And this is true at all times, so any time that's not equal to 0, I can cancel that way. The 1/2s can cancel from both sides. Even the minus sign can cancel from both sides. What it means is the weight of the first object divided by its mass is the same number as the weight of the second object divided by its mass. This ratio is a constant for any object near the surface of the Earth, and we're going to give it a little name. We're going to call this g. What it means is, if this is true, the weight of object number 1 is equal to this g thing times the mass of object 1. That's just multiplying by m1 both sides. It means that the weight of object number 2 is this little g times m2. The units of weight are newtons, and the units of what we have here are the units of g times a kilogram. So that's g times a kilogram is equal to a kilogram meter per second squared, which means that g is units of meters per second squared. And that is the little g that you are familiar with. G is 9.8 meters per second squared. It is the magnitude of the acceleration of this object as it is moving towards the ground. If I multiply it by a mass, by the mass of the object, then I get what its weight is. And this is a fundamental statement for how the gravity force works near the surface of the Earth. This little g is telling you about properties of the Earth, not properties of the mass 1 and mass 2. And figuring out where that little g comes from some universal point of view, that is something that we'll talk about in Chapter 3.